Welcome. In this video, I discuss linear maps and matrices. I consider a simple matrix with entries 1, 2, 3, 3, 1, 1. This is a 2 cross 3 matrix. I can multiply this with this vector, which we know is in R3, and the resultant from this product is 6, 5, which we know is a vector in R2. So, if I call this vector as x, this is b, then here what we have done, that we have multiplied x with a to obtain b. Or, in other words, we can say that with this matrix product, we have transformed this vector x from R3 to a vector b in R2. This vector x, which is basically in R3, is transformed into this vector b, which is in R2. And how this transformation takes place, that x is transformed with the help of this matrix product. So generally, if I have a field, say K, I can have vector spaces Kn and Km over this field, and I can transform vectors from this Kn to Km. I can define a transformation which is with the help of a matrix A, and the order of this matrix A, as we can see in this example, shall be m cross n. And how do we transform vectors from Kn into Km? Is that we pick any vector from Kn and we transform it like this, that La of x is basically equal to A times x. So this is the rule for transformation of vectors from one space to another space. And this transformation defined by this matrix is a linear transformation. Linearity, we know that a mapping is linear if it satisfies two properties, that L of xy is equal to L of x plus L of y, and L of cx is equal to c times L of y, where c is a scalar. So in this case, if I take any two vectors, say x and y, and I operate La on this vector, then by definition this would be A times x plus y. And now using matrix algebra, we know that this is Ax plus Ay, which is basically equal to La of x plus La of y. And hence, this first property is satisfied by this mapping defined by this matrix product. And similarly, La of Cx is equal to, using the definition once again, this is A times Cx, which can be written as C times Ax, which is C times La of x. And hence, this transformation defined here is basically a linear transformation. So, now we have a theorem. The theorem is it says that let A and B be m cross n matrices, and if La is equal to Lb, that is, the transformation defined by matrix A is equal to the transformation defined by matrix B, then A is equal to B. That is, if the transformation defined by two matrices are the same, then basically those two matrices are equal. And the proof is not very difficult. By definition, we know that AIX is equal to BI times X, because we know that the transformations are equal. Hence, every ith row of AX is going to be equal to the ith row of the product BX. So this is true for all I if where AI is the ith row of A and BI is the ith row of B. And hence, since AIX is equal to BIX, this would imply that AI minus BI times X is equal to the null vector. And this is true for all I and X. And if this is true for all I and X, we will have AI minus BI equal to 0, or AI is equal to BI, that is the ith row of A is equal to the ith row of B for all I. Hence, this would imply that A is equal to B, which is the proof of this theorem. Now, we know from the homogeneous systems that if I have a homogeneous system, AX equal to 0, we know that this can have trivial solution only or non-trivial solutions. And we have discussed one more feature about linear maps, that given a transformation from one vector space to another vector space, then we can define the kernel of this transformation is the set of all vectors in Kn, which are basically mapped onto the null vector. So this gives me the kernel of this transformation. Now, in terms of matrix transformation, if I have a transformation, say, from one space to another space defined by a matrix A, then the kernel of T, which is going to be equal to the set of all vectors in Kn, whose image under T is equal to 0, and we know that how T works in this case. This basically works like this. If it is determined by matrix A, then this is basically equal to this set, and hence the kernel is basically the solution set of the homogeneous system. So if I associate a matrix with a mapping, say T, then the solution of this homogeneous system gives me the kernel of this transformation.